Hello guys, today we are going to look at fractional distillation. So this is quite a lengthy topic, so this topic will be split up into 2 or 3 videos. So what is crude oil? Crude oil is a mixture of different hydrocarbons with different chain lengths. So it's just this black sticky substance that contains different lengths of different sorts of hydrocarbons, so when I say different lengths, when I say different hydrocarbons, I mean different lengths. And so majority of these hydrocarbons are aliphatic hydrocarbons. So crude oil is a fossil fuel. It is a sticky and tarry substance that is a complex mixture of hydrocarbons, mainly aliphatic hydrocarbons, and it does contain cycloalkanes and aromatic hydrocarbons. And crude oil is a finite fuel, and so it's non-renewable, and this was discovered 300 million years ago, and it was formed from the dead remains of vast number of tiny sea creatures and plants which sank to the bottom of the ocean and covered with layers of sedimentary rocks. Due to layers of rocks increasing, so did the pressure and temperature. So you had lots of rocks on top of this oil and on top of the dead remains, and so lots of pressure started to increase and the temperature also started to increase due to lack of oxygen. And so this converted the organic material into oil and gas, and the oil and gas were trapped under impermeable rock. So as you can see here in this diagram, here's the crude oil and it's being trapped by layers and layers of rock just on top, and so they use an oil rig to transfer all this crude oil from the bottom all the way to the top. So crude oil in its raw state is not very useful at all. In fact, it's near to unuseful at all. So it needs to be processed to separate out its valuable constituents, and the complex mixture of hydrocarbons is separated out into fractions by fractional distillation. So crude oil is heated until it vaporizes. So it's heated in this fraction column, and until it keeps on being heated until it vaporizes. And so the tower at the bottom is very, very, very hot, around about 350 degrees Celsius, and cooler at the top. And the largest hydrocarbons remain liquid at temperatures as high as 350 degrees Celsius, and they fall to the bottom of the column and are removed as residue. And the residue contains some very, very useful materials, and the smaller hydrocarbons rise up the column in the gaseous state, so all the lighter, shorter chain hydrocarbons are near the top. And as a particular hydrocarbon reaches the level in the column where the temperature is equal to its boiling point, it condenses and is collected in trays. Only the most volatile hydrocarbons reach the top of the column, so the ones that are most likely to evaporate very, very quickly. And the liquid formed is collected in a series of trays containing bubble caps, and the bubble caps force the rising vapors to pass through the liquid in the trays, and the vapors condense to liquid when they arrive at the tray that is sufficiently cool, and the liquids are then piped off separately. So here's a diagram for that explanation there. So here is a fractionating column, and as you can see, you have smaller molecules at the top, so the more volatile ones, and the larger molecules near the bottom. And like I said before, it's around about 350 degrees Celsius near the bottom, and it's extremely hot. And so majority of the residue lays at the bottom, and all the lighter stuff comes near the top. So you must memorize this. So you must memorize the trends in the fractionating column. So near the top, you have small molecules, so they will have a low boiling point. So they will have a low boiling point because as soon as they enter through here, they suddenly rise to the top. And they are light in color, so they're quite light. Pretty much anything near the top is near to see through, and it is easy to ignite, and it is very, very runny. And even if you memorize one trend of the fractional distillation column, you will be able to work out what the other trend is for the large molecules. So if we memorize, for example, just the small molecule trends, we can easily work out large molecule trends just by finding the opposites. So if small molecules have a low boiling point, large molecules with a will have a high boiling point. And since small molecules are light in color, they will be dark in color, easy to light, they'll be hard to light, and this is running so that large molecules will be thick. And examples of the small molecules would be things like refinery gas, petrol, naphtha, and then examples of large molecules. Long hydrocarbon chains will be things like fuel oil, bitumen, lubricating oil, and so on and so forth. So there are three main things you must include when talking about fractional distillation. That is the length of the hydrocarbon, the viscosity, so how runny or how thick it is, and the boiling point. So these three main points must come into when talking about fractional distillation. So then you can compare the molecules in the top end of the fractionating column and in the bottom, and so you then compare the lengths, the viscosity, and the boiling point. So that's it for today, and for the next video we'll look at more into fractional distillation. And if there are any problems or anything I can improve on, or if you like anything about this, please do comment down below.